Welcome, everybody. I think we should start, even though there's people still joining us. Thank you for joining us today for this Durham Energy Institute seminar. My name's Simon Abram, and I am Executive Director of Durham Energy Institute. As many of you know, I think DEI connects academics across disciplines and with external partners and funding for research on low carbon energy systems, and our research is independent, impactful, and relevant to real world challenges. So on that point, it's a real pleasure today to introduce one of our fellows, Professor Will Coombs, who is Professor in Computational Mechanics in the Department of Engineering at Durham University. And Will's published over 60 peer-reviewed journal papers in areas such as stress strain behaviour of soils, advanced numerical methods, fracture mechanics. His recent research looks at applications in offshore geotechnical engineering related to offshore wind energy, so including foundation solutions and issues related to cable installation. And these use a material point method suited to modelling problems involving large deformation and material failure. So today he's going to talk to us about risks to subsea cables. And for information, he's going to talk for about 30 to 40 minutes, so there will be time for Q&A after the talk. So please do add your questions to the chat, and we might call on you afterwards either to address the questions, or you might want to pose the question yourself. But in the meantime, we'd be grateful if you could make sure you're muted. And if you switch off your camera during the talk, then we'll invite you to switch them back on again for the Q&A. So with no further ado, I'm going to invite Will to deliver his talk. Will, over to you.
Okay, thanks for the introduction and thanks for the opportunity. I am very much an engineer and someone working in computational mechanics, although I have written this presentation for a general audience. It does include a couple of equations. We shouldn't be afraid of equations. They can't really hurt us, sometimes give us a bit of a headache. But yeah, it's deliberately aimed at a general audience, and I'm only really scratching the surface in terms of what we've been looking at. So if anything through the presentation is of interest, you'd like to follow up, please do so. And you can find me on the web easily, or you've got my contact email on the slide there. Now, I'm delivering the talk, but really there's a whole team of people behind the research we've been doing. All of the research in this presentation has been in collaboration with the University of Dundee, and I think I see Yassine has joined us, who actually did all the physical modelling as part of this project, and also the British Geological Survey, who did all of the seabed characterisation linked to this project, and the research all has been funded by UK Research Innovation. Okay, so a little bit of an outline of the presentation. I'll try and cover a bit of the background and motivation of why this is an issue and why we've been looking at subsea cables and how we can better protect them from anchor strike. Talk about sort of why it's important to bury cables offshore, how we do it, and how we specify how deep we should bury cables, and then look at some of the physical modelling and the numerical modelling that we've been doing as part of this project in order to basically better inform industry guidance on how deep we should be burying cables offshore in order to protect them, and then just finish up with some observations from the research, and hopefully about 35 minutes or so, 40 minutes, and then plenty of time for discussion. So a little bit of a background here. So I've been looking at problems related to offshore geotechnics, particularly focused on offshore wind, for about the last 12 years or so. So there are lots of processes that involve interactions with the seabed when delivering offshore renewable energy, and as I said, a particular focus on offshore wind. So really started looking at these sorts of problems back in 2014, where we looked at trying to model and represent seabed ploughing. So for those of you that are not aware, and this is relevant to this talk as well, in order to install a cable offshore, one common way to bury that cable beneath the seabed is to use a seabed plough. So this is a large machine that's dragged along the seabed, cuts a narrow trench which the cable goes into behind. And in that project, we were looking at how to provide better guidance on the forces involved, which goes into vessel specification, etc. We've also looked at things like foundation installation, so trying to model the installation of foundations, predict again force requirements, which goes into equipment specification when you're trying to deploy different foundation solutions of different sizes and different ground conditions. And more recently, been looking at drag anchors, so shipping anchors dragging along the seabed, how deep they penetrate in different soil conditions, and the associated risks to buried infrastructure, with a particular focus on power cables, particularly export cables, that are the cables that transmit the power from these offshore renewable energy installations back to shore. All of these research projects have been done in collaboration with the University of Dundee. They focus on physical testing, physical modeling of these sorts of problems, and at Durham University we focus on numerical modeling of the problems, and they really complement each other in terms of what you can explore. I think a few people who have joined haven't muted their mics, so maybe you could ask to mute because I'm getting a bit of feedback coming through. Thank you. Okay, so let's start by looking at motivation for this project. Why should we care about this? So here's a map of the waters around the UK. The sea is the blue bit, the light blue bit, and the land is the darker bit. Perhaps that's obvious. Now, what you can see by these white lines, these are actual individual pings from shipping traffic, and we can clearly see shipping lanes by these sort of white lines that have been traced. And if we just focus on one particular area, so an area of the southern North Sea, and we overlay on top of that subsea telecommunication cables, so data cables, and subsea data cables handle about 99% of global data traffic. Very little goes via satellite. And power cables. So power cables are shown by yellow, and you can see both interconnects, so connections between, for example, the UK and France, but also you can see export cables and inter-array cables for wind farms, offshore wind farms. And we can see it's a pretty congested sea state, seabed, if you like. And there are clear overlaps between the locations of these buried subsea cables and shipping traffic. And it's not uncommon for issues to occur. And this is only going to become more congested and more likely for issues to occur as we continue the expansion of renewable energy. So the sorts of things that can occur, so under storm conditions, ships that are anchored can drag their anchors, and this can then impact on buried subsea cables. So this is quite a historic case where under storm conditions, a ship dragged its anchor and damaged the interconnect between UK and France. But more recently, there's a real concern about deliberate sabotage and grey zone warfare. So this is an article from 2024 talking about deliberate sabotage damaging subsea cables. There's been cases of pipelines being damaged by dragging anchors. And even if you follow the right sort of press, people are patenting designs for anchors that are deliberately designed to cut subsea cables or damage subsea cables. And this is one from beginning of last year, but there have been others as well. So this sort of really motivated the current research that I've been leading and delivering in collaboration with University of Dundee and the British Geological Survey. So currently, if we focus on offshore wind, so we just focus on export cables for offshore wind, the cables themselves account for around 75% of all insurance claims associated with offshore wind. Now, that's not all due to damage through anchors or fishing activities. That's all insurance claims across the board. They are really a problematic element of offshore renewable energies. So when we lay a cable on the seabed, we can't just lay it on the surface. We need to bury this, certainly in shallow water beneath the seabed, in order to reduce the likelihood of that cable being damaged from fishing activities or through anchors or other things that move along the seabed. But burial depth is a real compromise. Okay, so going deeper, burying your cable deeper offers more protection, but it costs more, and it also causes other issues for the cable. So overburial is a problem in terms of thermal management of cables, and I know there are people on this call that know much more about this than I do, so I won't talk in any technical detail about that. But if we just look at damages to installed cables, anchor interaction accounts for around 70 to 80% of all power cable failures, and so that's data from March 2025. It does vary a bit depending on what cable type you look at and the period you're looking over, but it's usually in that sort of range in terms of the proportion of all cable failures that are caused, around 70% are caused by anchor interactions. So how do we actually install cables offshore? So here's one example. So this is a seabed plow. These things are pretty large. So we're talking about something that can bury cables up to around 3 meters in depth. So what happens is this thing is attached to the back of a ship. It's dragged along the seabed. These skids at the front can move up and down to vary the burial depth. The cable comes in to the front and it feeds along the device and then hopefully comes out the back at the bottom of the trench that's being cut by this plow share, basically. Now, depending on how deep you go, you need, or the deeper you go, the larger the force required to pull that plow along the seabed, and therefore the larger the vessel that's required, or the slower you have to plow, or potentially you have to do multiple passes in order to achieve a particular given depth. So going deeper, just the costs ramp up very, very quickly. Now, this is actually quite small in terms of offshore equipment. If we look at things like pipelines, those things become massive. So this is a pipeline plow, SMD pipeline plow. You can start to see the scale of some of these things that are dragged along the seabed. In this case, this cuts a V-shaped trench, and then there's normally a second plow, a backfill plow, which comes along and buries the pipeline. And when we're talking about cables, actually, if I go back to this image here, when you think about cables, don't think about domestic cables. These things, these offshore cables, are more like what I think about being a pipe. You're talking about something which is 250 millimeters in diameter. Again, there are colleagues on the call here that know this much better than me, but these are big electrical cables. They are not small cables that you would have in your office. So other options, we have things that resemble more like subsea tractors that we can use for mechanical trench cutting. So you might use these on certain ground conditions or seabed conditions, or between wind turbines if you need more control about exactly where you lay your cable. So this is an IHC particular subsea tractor. So this will go along the seabed cutting a trench again, which the cable is installed behind. And we also can use jetting operations as well. So this previous one was like a mechanical cutter, a bit like almost like a chain cutter sort of going through. Here we can actually use jets as well to fluidize the seabed and get that cable to drop into the trench. So there are lots of different ways that we can install them. And the equipment developed here is, I always think, amazing to do these operations. But the question always comes back to how deep do we go? How deep do we have to install these cables? And currently, the most advanced industry guidance is set out by the Carbon Trust. So it was laid out in 2015. And the overall framework is called a Cable Burial Risk Assessment Framework, or a CBRA. And there's lots of different pieces of information that feeds in to the assessment of how deep you would bury a cable. So on the right-hand side, what we have here is a cable route. So that's shown by the sort of the orangey, peachy coloured region here. The cable itself is marked out by these black markers. And all of these coloured lines, these are shipping traffic. And when you're completing a CBRA, or a cable burial risk assessment, what you would look at is you would look at the size of the vessels that are likely to be crossing the cable area. Therefore, you can estimate the size of the anchor that they would have. You look at the probability of them dropping their anchor, and based on both the probability and the size of the anchor, you then come up with basically a balanced assessment of how deep you should bury that cable in order to provide sufficient protection along the cable route, but not bury to an excessive depth that would cause other problems or be excessively expensive. Now, within this framework, you need to somehow estimate how deep a shipping anchor will penetrate into the seabed in order to then feed into that calculation. And here's, I think, one of 2 or 3 equations in the presentation. So the way that anchor penetration is estimated is it's based on the length of the fluke of the anchor. So this is sort of side view of a typical shipping anchor. We have the shank. This part will be connected to a chain or a rope going to the ship. And then the fluke. This fluke is the pointy bit, which will penetrate into the seabed. So they take the length of that fluke, they take the opening angle between the shank and the fluke, because these things can pivot as they interact with the seabed, and they use that along with a factor to account for different seabed types. So this is the sort of basic geometric equation. And they say that if you're in a sandy seabed, you take a value of 1 for this factor SF. If you're in a clay, you take a factor of 3. But if we look offshore, we don't just have sands and we don't just have clays. And if anyone here is more of a geotechnical engineer or a civil engineer, you know, even within those classifiers, and you probably know yourself, if you stood on a beach, that beach, if it's, you know, made of sand, can feel very, very solid, or sometimes it can feel almost like a fluid. You know, there's a huge variation in terms of seabed behavior, even within one classifier. You know, there's this massive range of also different soil types that we see offshore. And if we look at just, for example, one proposed cable route, so this is for a future floating offshore wind site. And if we look along the cable route, so this is where the wind farm array will be, and then this is the cable route corridor. What we've got here is markers, and they're coloured according to basically the seabed conditions based on grab samples going along this route. And we can see that we have a huge variation from gravels to things they call muds, basically clays, sand, sandy gravel, sandy mud. It's difficult to say, well, which do you take? Do you take that factor of 1 or do you take that factor of 3? And, you know, that's one site, but we look at another site off the coast of Scotland. Again, this is a future floating site. Again, this cable corridor, maybe a bit more consistency here, but we still have variations between sands, gravelly sands, muddy sands, even within these very short periods. And this is identified or acknowledged within the guidance document itself. It really says that there needs to be more guidance here. You know, seabed conditions are not simple in terms of just these two categories. And this is what we're trying to provide as part of this research project, is we're trying to provide more guidance on how deep is an anchor likely to penetrate in different ground conditions. And we're doing this through a combination of physical testing, which has been conducted at the University of Dundee, and as I said, Yassine, I think, is actually on the call today, who did all of the testing, and numerical modelling at the University of Durham, or Durham University rather. And all of this testing, though, has been guided by colleagues at the British Geological Survey, who have analysed thousands and thousands of cores across, particularly focused on the North Sea, and looked at what are the variations in seabed conditions, basically trying to bound the analysis that we're doing, both in terms of the physical testing and the numerical modelling, to make sure we're capturing the correct cases as part of this project. Now, the physical testing has been conducted in a geotechnical centrifuge, and probably for most of you, this is the first time you've probably heard of such a thing. A geotechnical centrifuge is just like a centrifuge you would use in chemistry, or a centrifuge that you would put an astronaut in order to prepare them for elevated gravity or elevated G levels. But instead, we use it for geotechnical testing, and I'll try and explain a little bit why we do this. But basically what we have here is we have a large machine, which is in pretty much a concrete bunker, where we have a box of soil, and we will run experiments where we will drag an anchor within that soil and look at how deep it will go based in different soil conditions or different seabed conditions. So during the testing, you know, we start off and everything's static like this. We then start to spin this machine up so that this arm is rotating round. And during actually the testing phase, this box of soil has rotated almost to 90 degrees, and then the tests will be done in flight at elevated G levels. And as I say, I'll explain the reason for this in a moment. So all of the testing is basically done in this configuration, and it's the elevated gravity that's keeping that soil against that outer wall of the box. And this is the typical test setup that we're looking at. So we have a model anchor, a scaled down anchor. We have a wire attached to that anchor, which is then connected to a shackle and a load cell. And this part is then moved during the test, where we're measuring the loads required to pull this anchor. And we're also measuring the trajectory of the anchor using a onboard 6-axis accelerometer with wireless communication and a battery all built into the back of the anchor itself. And just an idea of scale, you know, this is a conventional UK £1 coin. This is the size of the anchor that's being tested. And so the size of the instrumentation needs to be very, very small. We can't have anything like wires or anything like that connected, because that would change the trajectory and the motion of the anchor during the test. So we need to keep everything contained and everything transmitted wirelessly in order to not affect the results. So why would we do this? Why do we need to test anchors in a centrifuge? Why can't we just go into the lab, take our scaled anchor and drag it along some soil sample? Surely that would tell us what we need to know. Well, let's take the real case. So this is maybe the real anchor, full-size anchor. And if we consider what's happening within the soil, so within the soil, due to the action of gravity, we will have some vertical stress. So you can imagine that as we go further and further, deeper and deeper into that soil, all of the soil above is exerting a pressure on top of the soil below. So as we go deeper and deeper and deeper, that sort of vertical force, that vertical pressure on our current point is increasing, and it basically increases nearly linearly with depth. And it's given by, second equation, the density of the material, the gravity, so standard gravity, and then our depth into our soil body. So if we looked at, say, the tip of the fluke, we would have a given amount of stress, vertical stress here. However, if we then reduce down the anchor, say by half, and we have a look across, we can see that we'll have reduced our stress at that tip in the soil down by a half. And this is a problem, because what this means is that that smaller anchor doesn't experience the same ground conditions as the large anchor. And if we go even smaller, because bearing in mind that these real scale anchors, are a couple of meters in size, we need to go down to something which we can, is the size of a pound coin. We go even smaller, things get worse. So how can we counteract this? Well, what we have to do is we have to increase gravity. So here we've now got a new curve with an elevated amount of gravity to make sure that the stress in our original situation is the same as our smaller model that we're testing basically in the ground. So we're kind of tricking the ground to think the gravity's gone up, or it has gone up, and we can get then representative tests. So to say, if we go down to, a 20th of the size, we need to increase gravity by a factor of 20. And the way that we do this is we then, within the centrifuge, this allows us to then set the spin rotational velocity that we have to have in order to generate the right ground conditions. So here's the equation for, the acceleration in the centrifuge. From that, we can work out the angular velocity, and that then allows us to set the speed that we have to spin this box of soil at in order to get the right gravitational conditions. So we've got a box which is maybe a couple of tons that we're spinning at 80 RPM in this, so 80 revolutions per minute, so more than once per second going around in the centrifuge. And this is not particularly high in terms of the speed that this machine can go. Okay, so that's why it's important to do the testing in a centrifuge. It's basically so that we get the ground conditions correct as we scale down that anchor size. Otherwise, there's a risk that it could change the kinematics of the anchor and therefore how deep it goes during the testing. Okay, so what can we measure? Well, typical things we would measure in the geotechnical centrifuge would be how deep does an anchor go? So here we have a plot of the drag. Now these are all scaled back up to the real size. So dragging of 16 meters, and depending on the ground conditions, we see very different penetration depths. So here at the top, these are all in sand. We have a very dense sand, a really quite hard sand to penetrate, going all the way down to something that's very loose. This is something that you'd almost sort of, if you tried to stand on it, you would almost sort of sink through. You could easily just push your finger into the sand bed in the lab. And we can see that we're varying in terms of the penetration depth from something which is around 0.5 meter down to something which is more like 4 meters. But if you go to the industry guidance, they say that it doesn't matter what sand you should have the same penetration depth, which is clearly not what we're seeing. You can also look at things like the forces involved as well, and this is useful if you want to, so people that sell anchors, characterize them in terms of a holding capacity and things like that, so we can also do that, but that's less relevant to this particular research project. So the geotechnical centrifuge is great in terms of it provides us with a rather limited number of cases, which we can then use to validate the numerical modeling. So this is like our ground truth for then the numerical models that we develop. So that's the other half of the project, is looking at the numerical modeling. So Modeling this problem is quite challenging. So you're trying to model the penetration of an anchor as it drags along the seabed, and you're trying to represent all of the physics that are going on. And at the moment, there are no commercial codes available that can do this robustly and reliably. So at Durham University, we focus on developing new numerical methods using in-house codes that can model these sorts of very large deformation problems. And really what we have to worry about is we have to worry about the deformation of the seabed, and we have to worry about the contact mechanics between the anchor and the seabed. So what's going on at that contact interface. And we use a particular method called the material point method. So for engineers on the call, the material point method is very similar to the finite element method, but it allows for the modeling of very, very large deformation problems without some of the issues you encounter if you try to do that with conventional finite element analysis. Within this method, we have points. So these sort of spheres you see here, and these are trying to represent the seabed. They're not particles as such. They're like lumps of seabed that we're trying to represent. And we have a computational grid that we use to do all the calculations on. I won't go into the details particularly. So what that looks like in terms of if we just have an anchor that we place on the seabed. So this is a hall anchor. It's one of the most commonly used shipping anchors, so a Navy stockless style anchor, is under gravity. The points will deform around the body, and also the computational grid that we're using to solve all of our equations for this will change and adapt such that we get a good representation around the anchor as it's just coming to rest. Once an anchor is then at rest, we then look at dragging it along a seabed. Now, this is a different anchor. This is an AC-14 anchor. This is probably the other most commonly used shipping anchor. And what we're doing with the numerical models, again, we've got the computational grid for the calculations. We've got the points that represent that are forming seabed material, is we allow that anchor to drop and then we drag it along. And we're basically replicating what we did in the geotechnical centrifuge, but digitally using a computational simulation. Now, these simulations are expensive. We run most of them on Hamilton, the university's supercomputer. They typically take around 5 days each. Now, I raise this point because there's also a CO2 cost associated with each one of those simulations. The simulations used to take around 50 days each, and we worked out the CO2 cost of that, and it was equivalent as the same CO2 cost as a flight from Paris to Dublin and back for a single person. And we then spent a lot of time trying to reduce down the cost of those simulations, both in terms of run times, but also in terms of energy usage. So we've now got to the situation that rather than taking 50 days, it's taken 5, and the CO2 cost, rather than a flight from Dublin to Paris and back, is now 2% of a single flight for a single person. And I don't think this is talked about enough, actually, in terms of the cost of doing numerical simulations, in terms of the CO2 impact and the energy cost of each of those analyses. Okay, so maybe one thing to mention, okay, this is a little bit of a side. The particular method we use here is the same numerical method that Disney uses to animate films like Frozen, which is quite a fun thing. It's quite interesting for me because I have to then keep an eye on the computer graphics literature as well as the engineering literature for this particular numerical method. But when you see, I'm sure you all love the films. My daughter's, well, one of my daughters is obsessed with Frozen. But all of that snow movement, that slow deformation, it looks pretty realistic because it's underpinned by a numerical method that's actually trying to represent the correct physics. And as I say, it's exactly the same simulation tool. If you're interested, if you just search for, Disney animation, they have some great, really accessible videos of trying to explain how these methods work to, young people, basically, the simulations behind the animations that they're producing. So it's just sort of a bit of a fun fact. Okay, so how do we actually then run and get reliable results from our numerical methods? Well, first of all, we have to make sure that we've got the ground conditions right for an anchor test. And the standard geotechnical site investigation they would do along a cable route is something called a cone penetration test, or a CPT. So what they do is they go along and they push a conical tipped rod into the seabed and measure the resistance to pushing that in. And so what we do with our numerical modeling is, first of all, we check we can get a good representation of that test to make sure our material properties are correct. So here are the sorts of plots you would get. So for a given penetration depth of this rod into the seabed, you measure the resistance to pushing that thing in. We have experimental results, again, from the University of Dundee, and we then try and predict that response. But then what we do is we tune our numerical parameters to make sure we get a good representation. So here we now have the same 4 seabed conditions we saw previously from the centrifuge testing. We get a good match between our numerical method and the physical testing. And then we fix our parameters and we don't change them at all. The model is now set. And then we predict the anchor penetration. Because it's fine if we could match a case, but unless we can predict these cases, the numerical method is almost pointless, really. So here's, again, sort of simulation we might run. We've got a Hall anchor and an AC14 anchor. And what we simulate, again, is that dragging process, that penetration process. And what we see is actually very different penetration depths for these 2 different anchors. They have a very similar fluke length, and the guidance say that in the same ground condition, they should penetrate the same amount. But what we see is the AC14 penetrates much, much deeper than the Hall anchor, but the Hall anchor has a longer fluke length. And Ria should credit Yassine with this, saying that the thing that's stopping the Hall anchor penetrating are the large ears here behind the fluke, which really resist a lot of penetration. So we can then compare our numerical models with the results from the geotechnical centrifuge. So the numerical prediction of the anchor penetration based on drag distance is shown by the continuous lines. The final depths achieved by the physical testing is shown by these discrete markers. So pretty good predictions, particularly in terms of loose sand and very loose sand. So where we're getting the most penetration depth. Here, the depth is normalized by this fluke length, as is the drag distance. That's the Hall anchor. Similar plot for the AC14, and you can see this dramatic increase in the penetration depth. And just to highlight that this is the industry guidance document prediction. It's saying that all anchors in sands should penetrate this deep into the seabed. And we can see that in some cases it's conservative, but in many cases it's not conservative. And maybe those cables are at a greater risk than is estimated by the industry guidance document. And so if we just overlay those 2, just changing your anchor type, but basically keeping the fluke length the same, you see a 30% increase in the penetration depth moving from one type of an anchor to another. And this is quite problematic because you often don't know what sort of anchor is actually being carried on a given ship. So these are sort of just reproducing the physical test results. But the nice thing about numerical model is once it's been developed and it's been calibrated and validated against something else, you can then start exploring all sorts of different things. And one of the things we looked at, well, what happens if you change the size of the anchor? The guidance document says that if you double the length of your fluke, your penetration into the seabed should double. And equally, if you half the length of your fluke, the penetration should halve. And so here we've just rerun the simulations with 4 different sizes of AC14 anchor. So if this was the original one, we doubled it and increased it by times 3. And we also halved the size of the anchor as well. And we looked at then the penetration depth achieved in different ground conditions, normalized by the length of the fluke. And what we're seeing in the loose ground conditions, so that's the red lines, we're basically seeing the same curve no matter what size the anchor is if you've normalized by the length of the fluke. So this is confirming that the idea in the industry guidance document that if you double the length of your fluke, you get twice the amount of penetration. Now, the very dense sand seabed condition looks a little bit different. We see a bit more variation, but in the limit, they all tend to the same response. What we're interested in is what's the ultimate depth that these anchors are going to achieve. And this difference here can really be attributed to when the anchor fully opens and bites into the seabed. If you look at the fluke angle, so the angle of that fluke, the loose cases, it's all the same. But the very dense case, your anchor starts to bite at a different point, and then they trend to the same response, which is why we just see this bit of difference initially in the very dense, the very hard seabed, in terms of the penetration, but then they all end up trending to the same result. So we are able to confirm through the research this idea that it's just linearly dependent on the length of the fluke, which is not necessarily obvious, because if you double the size of your anchor, your mass goes up by a factor of 8 of that anchor, or the weight of that anchor goes up by a factor of 8. So we weren't entirely sure if this was going to come true, but this is something that we did manage to confirm. The other thing we can look at, and actually I'll just skip over that, is we can look at what happens when you have layered combinations. So what happens if you have a sand above a clay, or a very dense sand above a loose sand, or a very loose sand above a very dense sand. We can then start to play with this parameter space and look at actually what happens, because layering of the seabed, and this is very, very common, that in the near surface, a seabed has multiple layers of different materials. There's no guidance at all currently available to industry on really how we should deal with these scenarios. So again, this is something we looked at with physical testing and numerical modeling. We looked at very loose over very dense and some other combinations. We did the physical testing. We got some ultimate penetration depths. We then repeated those tests with the numerical models, and we got a very good match for the 1 meter of very loose over a very dense seabed, and a pretty good match for the 0.5 meters of very loose over a very dense seabed. But we can then explore lots of other cases as well. So we can look at lots of other combinations in the numerical modeling that would be difficult to do in the physical testing. And really overall, the conclusion from this is that things are pretty complicated. It's not an entirely clear picture. Exactly what will happen in different conditions. And this is an area that we've identified where there really needs to be more research and more guidance that we're continuing to work on to provide really advance on the state of the art and the advice given to industry. And we can also repeat this for different anchor types. So if you compare AC14 and Hull, when we have a shallow amount of very loose sand over very dense sand, the response is very similar. But once we have larger layers of loose material, we start to see a much bigger difference between the different anchor types. And here we have a 20% difference in the penetration depth. And really, according to industry guidance, these should be penetrating the same amount into the seabed. Okay, so I'll finish up here. Hopefully that's around 35 minutes or so. So overall, what we found in the research we've been doing here is that the industry guidance is conservative in some cases. So in very, very hard seabeds, actually, anchors are not going to penetrate as deep as is assumed, and we can maybe potentially reduce the burial depth of cables slightly, which has benefits in terms of cost and potential overheating of those cables, while still offering the same amount of protection assumed in the guidance. However, if we go into softer seabeds, loose sand conditions, anchors penetrate much, much deeper into those seabeds than is currently really estimated by industry guidance. And that means that the level of protection we think we have of those cables is less in reality than is assumed as part of the design process. One of the things which is not taken into account at all is the geometry of the anchor. You purely look at the length of the fluke. You don't take into account anything else about the anchor. And we've shown that geometry is really important. It's particularly important for loose sand conditions. And we should be trying to move to making more of assessment based on anchor type, not just on fluke length. It's been good that we have managed to confirm some things about the industry guidance, particularly about this scaling. And layering is really complicated. Design ideas are coming out all the time and how you can potentially account for layering, but there needs to be better guidance for industry on how to deal with layered combinations. Because if you speak to one consultant or one developer, they may have developed an in-house way to deal with this. Another consultant has developed another in-house way to deal with this. And the problem with that is that there needs to be some agreed methodology, because the person that designs the cable is not the person that installs the cable, is not the person that ends up owning the cable or operating the cable. And there really needs to be some agreement here such that there is a shared risk and a shared acceptance of risk across the industry on these assets. So there's a lot of work to be done here in terms of layering. And sort of finally, just to say that I've acknowledged, that there was a lot of work done at the University of Dundee and a lot of work done at the British Geological Survey as well, underpinning this project. But at Durham, there's been a whole team of PhD students and postdocs that have worked on these numerical methods over the years, from Tim Charlton, who was very much the guinea pig in terms of using this method during his PhD, through to Robert Bird, who's the person that's developed our current modeling code and capabilities. If you're interested, this QR code will take you to some project web pages where you can see publications and other bits and pieces. We're also using the same techniques to look at mooring anchors for floating offshore wind. So this is a high performance drag embedment anchor as part of a Northern Net Zero Accelerator project that we've been doing as well. Same techniques, just with a different focus in terms of capacity of these anchors rather than necessarily just how deep they go. So with that, I think I'll finish and hopefully that gives some time for some questions.
Thank you very much, Will. That was really fascinating and admirable the way that you've moved us from very much core research to applications in a really helpful way. Thank you. And we've got some questions coming in already. Please do add your questions into the chat. And just before we jump into those, I wondered if you could maybe just say something about how widely varying anchor design could be. So like what's the scope of the further research you'd need to do to take account of those different designs?
Actually, thankfully, anchor designs are reasonably unified, actually. And the Hall and the AC-14 anchor are by far the most widely used anchors in the industry. But what we don't know necessarily is, for a given ship, what anchor it's carrying. And that's, I think, the issue. I'm sure, though, with image processing, Gen AI, things like that, that actually we could probably pretty quickly actually develop that database to know what anchors different ships are carrying. But I think that's the main issue, is because there's no problem in terms of rerunning analyses with different designs of anchors, but there are not that many different ones. It's just the current guidance doesn't take that into account at all. Basically, that's the issue.
Thank you. So there's a question here from Ray asking whether the soils in the centrifuge models are saturated.
So yeah, this is a really good question. It depends on the tests, right? So the ones I showed in this presentation, no, they were dry, but the drag rate is deliberately kept low, and we're basically looking at the worst case fully drained scenario. I assume, Ray, based on the question, you're probably geotechnical person, or at least some knowledge there. So we're assuming fully drained conditions, so any pore water pressures would fully dissipate immediately, and that is like the absolute worst case that you would have in terms of penetration. We have run, or not me, Yassine, who is on the call, I think, has run tests under saturated conditions, but doing saturated testing in a centrifuge is actually quite tricky because you have to scale other things about the fluid as well. You can't just use water. You have to use different fluids to get the pore pressure relationships correct and things like that. You basically have to play with the viscosity. And we have done that testing as well, and we find that as you do it saturated, the faster you go, the less you penetrate into the seabed, which is expected. But actually, it's in the looser conditions where it has the most effect, which is counterintuitive from a soil mechanics perspective. And we think it's because of drainage paths. You're basically deeper, so there's further for that fluid to have to drain to the free surface. So the answer to your question, we've done both. And sorry, that was a very waffly answer, but yeah, we've looked at both. And if you go to this QR code, you can see publications where we've covered that other testing.
Thank you. And Matt here is asking what you've done in terms of looking at mixed sediments like muddy, sandy gravel or varying D50 within a sediment class.
We haven't yet. So we've looked at single type of sand, different relative densities, and we've looked at a couple of same clay but prepared in different ways, so varying the undrained shear strength. But we haven't looked at lots of different combinations of different sand conditions. What we're trying to do, again, it sounds very much like this is a geotechnical engineer asking the question. What we're trying to do is tie everything back to cone penetration tests, basically, rather than individual different types of soils or D50s and things like that. And the reason for that is because we often just wouldn't have the full characterization of the seabed sediments along a cable route. So we're trying to keep this as usable as possible for real world applications. Oh, and great. I just see Yassine's reply to, oh yeah, about the gravity scaling thing to do with the pore pressures and things like that as well. So thanks, Yassine, for covering the thing about the centrifuge testing.
Thank you. Would anyone else like to raise a question? Here's a question from a different Matt. Can you see the questions?
Yes, yeah.
Yeah.
Yeah, so how many material points? It used to be we were dealing with low millions of material points in a given simulation. So these are the discrete points representing the soil. We're now actually, because some of these simulations looked a bit different. So I'll skip back a little bit. So here you can see we have a pretty much a uniform distribution of points. This was our old numerical model, which took about 50 days to run. We've now moved to something which automatically adapts, which is like this, which was the video I showed earlier. And this means that we've dramatically cut the number of points we actually have to consider on our simulations. And what we do is just as the anchor comes close, we automatically refine the number of points that we have, and without losing any accuracy in the simulation, because actually far away from the anchor, very little is happening. And so we can just concentrate. It's a bit like when you do finite element analysis, you concentrate your small elements around the areas of interest. Same idea here. We concentrate our points, and that's cut down from having millions of material points to, a few hundred, tens of thousands, 100,000 points. And it's made it, a dramatic improvement in terms of the run times. But also the mesh we use for the calculations has far fewer points in it as well. And that's helped massively in these sorts of problems.
Thank you. I think Abhishek is asking a sort of clarification question about these guidance being more or less conservative.
Yeah, okay, sorry, I'll just try and read the question.
So do you think the current cable burial anchor penetration guidance is overly conservative in some conditions while being insufficiently conservative in others to reliably protect subsea cables?
Yes.
Yeah.
Yeah. Yeah. And I think but it is quite a nuanced picture though, this, because we are focused on one element of a cable burial assessment. We're just looking at, in a given seabed condition, how deep does an anchor penetrate? And that's one ingredient into this calculation. But a major ingredient into the calculation, there's this, it's called like P strike, the probability of a strike occurring. And that's based on that information about how deep an anchor goes, but also about the distribution of the shipping traffic, about the probability of an anchor dropping, a ship dropping its anchor and then dragging it across the cable route. So we might find that these anchors penetrate, twice as deep as the guidance suggests, but that doesn't mean that your risk has doubled, because there are lots of things coming in here. And it's only if you had that scenario of that particular vessel crossing that cable at that time, deploying its anchor, that it would then damage the cable. So yes, I think your statement is correct, that in some cases we are over conservative, in other cases probably entirely appropriate, and in other cases we're under conservative. But what I think we don't have at the moment is a good idea of that distribution of conservatism or not across a cable. And I think that's where these models help. Obviously, they're going to help in terms of future cable deployments, but they also help us to understand the risks on our current network and where we might need to go in and do some remedial action if we think there's a particular vulnerability, because you can do things like rock placement or other protection methods as well.
Thank you. Yeah, we've got a couple of questions here from Sophie. First, asking if you've given any feedback to the Carbon Trust. And secondly, well, perhaps we'll read this out. The second is in terms of understanding the seabed conditions in the first place, we see a lot of misunderstood soil conditions, especially with variation along the route and seabed mobility. Did you look at any recommendations like the number of CPTs or boreholes and how many and so forth?
Okay, so well, hi Sophie, nice to see you join the call. I hope you're doing well. So we know that the Carbon Trust, or as I'm aware that the Carbon Trust is currently consulting with lots of stakeholders about a revised CBRA approach. I'm aware things are going on that. Pretty much there isn't a week where I don't give a talk to a industry stakeholder on this research, mainly developers, but also geotechnical consultants, some contractors, etc. So trying to spread this as much as possible. I know that the Carbon Trust are aware of our research and what we've done here, and ideally, what we found would have been incorporated into a revised CBRA process, so a CBRA 2.0, if you like, and that would be the ideal scenario from my point of view in terms of impact of what we've done in this research project. We set out trying to improve industry guidance, and we want to see this through to completion. So we're working on that basically. In terms of site investigation, we haven't specified any particular recommendations. From my viewpoint, the more you have, the better. There's always a cost implication. The standard is basically, as I understand it at least, is a cone penetration test at 1 kilometer intervals along your cable route. Can be a bit less than that sometimes. So yeah, I think the more the better, really, within reason. Not expecting boreholes along a cable route, to be perfectly honest. And you're only interested in the near surface anyway, really. So,
Thank you. And we've got time for a couple more questions if people would like to drop something in the chat or raise your hand. Here's a question about the specifics about how you're modelling the interaction between the anchor and the soil.
yeah, sure.
How specific
Okay.
you want to go, but
Yeah, I can go very if you want. So,
moderately maybe.
okay. I won't go, I'll just outline the basic thing that we're using. So this is probably the most relevant image. So we basically have a penalty. The nature of the question, it sounds like you're familiar with numerical methods. So we have a penalty condition between the material points representing the soil and the anchor, which we represent as a rigid body. The penalty constraint is defined on the rigid body because we have a discretized shape, but we basically have an STL, like a triangulated surface for the rigid body. The contact detection is based on a domain associated with each point. So we track the corners or the vertices of each of those domains. And when they interact, we have then a penalty constraint, which is basically like a spring trying to push that point so it has a proper contact condition on the surface. It's a frictional condition, so we can vary the coefficient of friction between the soil and the rigid body. Actually, we find that doesn't have a big impact on the results unless you have no coefficient of friction. If it's zero, then it has a big impact. A lot of...
Sorry, I think we've got a non-muted person. We just put mute them. Okay.
Okay. I mean, yeah, hopefully that's sufficient, Matt. I mean, feel free to follow up with me if you want more details on the technical side of things we've done. It's also all detailed in the papers associated with this project.
Thank you. So, okay, two more questions. First, Alex, have you considered how anchors may interact with non-uniform burial on the route, particularly partially backfilled or open trench sections after penetration depth, etc.?
Yes, we have looked at that. And again, this work was done by Yassine. So the work they do at the University of Dundee is absolutely fabulous. And I'm horrified about what I'm hearing in the news at the moment with the University of Dundee, and really feel for colleagues there. So the equipment that they do, I mean, bear in mind that they're doing this testing in a bunker, in a box of soil that's being spun at like 80 revolutions per minute, more than once per second. This massive box is going around and things like that. But what they can do is they can do a ploughing operation simulating the installation of a cable, a backfill operation, so they can take, for example, like a pipeline plow, drag it through, a backfill operation, and then drag a cable through it all in flight. And they've looked at what happens if you drag perpendicular to your cable route, so going straight across. What happens if you go at 45 degrees, and what happens if you go directly along? Good thing for cables, unless you go directly along that line, there's very little impact. Okay, it's such a thin slot that you cut that basically the anchor maybe blips and then just carries on. There's almost no effect. Pipelines are quite different. That backfill material is very, very loose, and you see real changes. You see the anchors dive, again, particularly if you're following the trench that you've cut and backfilled. So yes, we've looked at that. We're currently trying to publish it. We hope it's going to be out soon. But yeah, that has been looked at. And we've also, which I think is of interest based on the nature of the question, is we've also done cone penetration tests through that backfill material as well to try and quantify its properties, which obviously you can't do if you've installed a piece of infrastructure. You can't come along and then stick a probe through your pipeline or your cable, but we can do it because there is actually no cable or pipeline there. So we can put a probe through and measure the soil properties of that backfilled material as well. So that might be of interest. Jenny's question on Disney sequel.
Yes, we could possibly take these two together because what's next? For example, any more uses of the model?
So there's lots of different uses of this modeling that we're doing. So one thing we're doing is we're looking at, as I mentioned at the end, we're looking at mooring anchors for floating offshore wind. So seeing how they behave in different ground conditions. We're also trying to look at optimizing the actual anchors themselves as they're scaled up. So how big you make the various plates to make sure that the anchors themselves are going to survive in different ground conditions and things like that, how they respond under repeated loading in terms of fatigue. This work with the anchors, we've got a proposal currently under review. It's been under review with UKRI for 7 months now. Hopefully we'll get the reviewer comments soon on extending this work to also look at the interaction with cable protection. So I mentioned at one point in the presentation that you can use things like rock dumping to protect cables offshore. So if you have particularly problematic areas, so for example, when you have two cables crossing over each other, you can't just plow through and put a cable through another cable. You have to bring it to surface, transition over and rebury again. So in those crossing situations, you would use, other protection methods. So we're trying to extend what we've done here to also include the rock protection or the concrete mattressing that protect the cables, and look at the interaction of the anchors with that. And if they actually provide any protection, I'm dubious, but yeah, okay. We're loads of things, to be honest. Anything that involves rigid bodies interacting with the seabed or near rigid bodies. We're looking at installation of different types of foundations as well. Lots of different things. Depends on the funding source. Oh, we're also using the same methods to look at decommissioning as well. So how do you get, monopiles back out the seabed? What are the force requirements? What are the different options for actually doing that? Because this is coming, in the next few years, we're going to have to decommission some of our earliest offshore wind sites. And then in, 10 years, 15 years, we're going to have to be taking things that are massive out of the seabed. And currently, there's no option. Currently, it's specified that these things have to be removed. But is that even feasible? So, yeah, there's lots of things we're looking at.
That's great. Well, thank you for a brilliant seminar. And it's nice to know I'm not the only person who's looking forward to the Disney sequel. Thanks, everyone, for joining us, and keep an eye out for our next seminar coming up soon. Thank you again to Will.